Hi, I am Mackenzie Pulka with the Shape Senior Design Team. I am the Extrusion role, and my team members include Skylar Patten, Braeden Apps, and Jonathan Rixstine. We have been working to optimize aluminum extrusion texture for improved bendability. Shape manufactures aluminum extrusions for car frames and is trying to improve the energy absorption of electric vehicles to better protect passengers and battery in side impact collisions. The industry standard for measuring the energy absorption for extruded aluminum is the VDA bend test. This test measures the bend angle of a small sample to easily quantify the energy absorption across different size samples. Cracking at the bend radius sharply decreases energy absorption. Therefore, we want the part to bend further before cracking. We are looking at 6005A aluminum, which is an alloy that is strengthened by Mg2Si and has aluminum, manganese, chromium, iron, silicon dispersoids to improve extrusion. We cast and extruded our own 6005A compositions to make the bend samples. We use a pusher billet to push out the 6005A billets and use the middle of the resulting extrusion. Extrusion influences the texture of 6005A aluminum. The texture is the distribution of grain orientation. There are 001, 101, and 111 crystal orientations, and every orientation in between. These grains make up a distribution of organized grains to make texture. We are looking to get more 001 texture to accommodate larger strains for side impacts. We hypothesized that if we change the ratio of chromium and manganese in the casting of 6005A aluminum, then we will see an increase in the cubic crystal texture after extrusion and larger bend angles. This is because different ratios of chromium and manganese will affect the size of aluminum, iron, manganese, chromium, silicon dispersoids. The coarser of the dispersoid will facilitate more cubic texture.
Hello, my name is Jonathan Rixstine. I am the characterization lead for this team, and we ran thermocalc simulations to see the size and distribution of manganese and chromium dispersoids. We found lower chromium and manganese dispersoids yielded coarser dispersoids, and higher composition yielded smaller dispersoids. However, the high composition had larger volume fractions than the lower compositions. From this, we designed an experiment to test the energy absorption of six of the compositions that we ran in the simulations. And we found that the high chromium and low manganese compositions yielded the best energy absorption. Our samples were too thin to get bend angles from the VDA test, so we used the area under a force versus displacement curve to 10.5 millimeters of crosshead travel to normalize our results. In conclusion, increasing the chromium concentration increases the dispersoid size, and we hypothesized that it increased cubic texture and therefore improved the bendability and energy absorption of the 6005A aluminum. And our next steps include analyzing the texture of these bent samples, increasing the bend sample thickness so that we can get bend angle, and changing the extrusion die for deformation. And we would like to thank our Professor Paul Sanders. We'd also like to thank our sponsor, Justin Clark, and these faculty members for helping us with all the things that we needed to do for this project. Thank you.